Session about data assimilation methods. In the first part and the second part, we covered basically where we are, state of the art now. So, 4dvar is used. I think you saw examples of 4dvar being used operationally in the US, in Hawaii. Also, it's used operationally. The low-rank extended Kalman filter is used also operationally in Mercator. I'm not aware if any center is doing now Ensemble operationally, Kalman. Is there any Ocean center doing that yet? So, or at least people are working on that to go to Ensemble Kalman filtering. The last session is about just open questions. We're working on it. We're not there yet, and we're trying to advance and improve the methods we have. So each part can be a session by itself. Okay. So basically what I decided to do is to focus on the non-Gaussian filtering. It's hot these days. So there will be most of the session on the non-Gaussian filtering. And then I'll have 1 or 2 slides for each of these topics. Each of these topics can be a PhD by itself. They are not applied on ocean large scales yet. And we are interested in it. If anyone of you guys or someone who's interested in working on that, we'll be happy to do that. I'll show you at the end just our plans, what we are planning to do in the Red Sea with regard to this. Okay, so let's start with the non-Gaussian filtering. As I discussed in session 2, the Ensemble Kalman filters, they assume a Gaussianity at the analysis step, even though the forecast Ensemble is not Gaussian. So what we're trying to do is to upgrade and go to Gaussianity. Why we want to go to non-Gaussian distributions? Because the ANKF so far, in the few kilometers, it's working well actually, and we want to try to improve it because the ocean models are becoming more and more nonlinear, and when the models are becoming more and more nonlinear with high resolution, with data observing at the kilometer scale, we're seeing more and more scales that are nonlinear. And so the distribution will become more and more non-Gaussian. And the question that is not clear yet, will the ANKF be as efficient as at these scales? Okay? On the other hand, we are also trying to see if we can improve upon the Gaussian assumption. So basically where we are now, this is just the Red Sea. I like this figure where, coast is somewhere here. We call this the coast eddy. This is ocean color. And you see these structures, very nonlinear structures from data. And actually there is an eddy here. There is a very interesting phenomena because it's not an eddy that's supposed to pump chlorophyll from down. So something is just, this eddy is just steering chlorophyll around. And the chlorophyll are coming from somewhere. Anyway, and we're having models now that are resolving more and more these kind of scales. This is a 2-kilometer model, but now we're running 300 meters resolution. So if we even see more scales, this is just fresh water coming from the Indian Ocean toward the Red Sea. So the processes are much, much more nonlinear, very small scales, and which means that distribution will be non-Gaussian. And can we do something about it or prepare ourselves to get there? So the question is how to build efficient non-Gaussian filters for high-dimensional systems with small ensembles. Small ensembles, even 1,000 is a very small ensemble to answer the questions that have been asked. In principle, there is a theory behind the non-Gaussian filters. And then they show that the number of particles, members, ensembles, the size of the ensemble will increase exponentially with the dimension. So if you have 10 to the 8 dimension, exponential 10 to the 8, this is how many members you will need. Okay? So this is the dilemma we have to deal with. Just to show you ahead of where I'm going, that we compared the particle filter, I'm getting there, with an Ensemble Kalman filter with a system that has 2 scales, slow scales and very fast scale, very simple model. And I wanted to see if the now Gaussian brings something to the table. Okay? And what we see is that the ANKF gets the large scale pretty well, but the fast scales, the ANKF, when there is not enough data, it just doesn't get it, while the non-Gaussian filters, they are still more or less getting it. with a very small system. Okay? So based on that, we think that the non-Gaussian filters can bring something to the table, and we're trying to do it. But we have a very, very important constraint, which is we have a small ensemble, limited, let's say the word limited ensemble, and limited number of samples. And we are in a huge dimension. So, it's pretty hopeless when you think about it. Okay? So the theory of non-Gaussian filtering is well established, and there is proof of convergence. A particle filter, it should converge to the true PDF. But this is under the limit of infinite ensembles, infinite number of particles. But we have the constraint, we cannot do that. Okay? And another important thing I will discuss quickly is that resampling from the distribution is very important. Otherwise, all these particle filters will not work. So more on that later. And the question how we do that with small ensembles. Okay, limited, maybe a better word than small. And in my opinion, thinking about this problem, there are two main two things that you need to be care about. If you have a small ensemble, a small number of particles, you have to think about a pragmatic way to parameterize the PDF. Don't think that with 100 members, a PDF in a dimension 10 to the 8, you can represent it by histogram. I'm getting to that later. And the second thing, you have to be careful on how to resample. You have a big PDF. You cannot just, in a big dimension PDF, you cannot just resample randomly and hope you will represent all of it. There is no way. Okay? So you have to resample in a smart way. And this is what we're focusing on. Okay, so just give you an example. Take this optimal filter we talked about before. I'm updating PDFs. Okay, and I want to implement it. Okay, to implement it, we need to discretize it. So in the eNKF, we assume that it is Gaussian. Okay, the red is supposedly the PDF that is non-Gaussian. Okay, another way, a better way to describe the PDF is to use histograms. We call this Dirac mixture of Dirac functions. Okay, you have a particles on some members, and each one has a weight, and it describes a PDF in a much better way, approximates than a Gaussian, of course. But you need many of these. Okay, this is in 1D. Another way to represent the PDF is to use a Gaussian mixtures, which is sum of Gaussian. So you see these 3 blue Gaussian distribution. I sum them up and I get the red. So I can use less component of Gaussian in the mixture to represent the PDF than Dirac mixtures. So if you take these, okay, and you represent the PDF somehow according to this approximation, then if you take the forecast step, let's say, okay, in a forecast step, if you take a bunch of points, okay, the PDF, and you integrate it, you just integrate it with the model. This is the Dirac mixture Monte Carlo update. Okay, if your PDF is histograms, numbers, just propagate it forward in time. This is what we use in eNKF. You can also assume that this is Gaussian mixture. So you have 2 Gaussian, and what you can show is that you're updating each Gaussian separately. So basically, you're running 2 ensembles that are separately, and this becomes a little bit heavy. So we'll get stuck to this one. It's working well. It's just I have a bunch of members, and I'll update them forward in time. Okay? Now, if you get to the analysis step and you assume it is Dirac histograms, then we get what you call the particle filters. And what particle filters are doing basically is just updating the weights of the particles. They are not touching the particles. So every time you have a data, you're just updating the weight of the particle. And basically what's going on, the closer the particle is to the data, it gets more weight following a Gaussian shape because the Gaussian is the likelihood of the observational error. Okay? So it doesn't touch the weights, it just updates the particles if you follow a Dirac mixture. If you assume it's Gaussian, you get the eNKF. This is what we talked about. Okay? You have Monte Carlo plus Gaussian. Now, if you assume a Gaussian mixture, you get these 2 at the same time. So you get a Kalman correction for each center of the Gaussian mixture or component of the mixture, and you have a weight for each Gaussian component. So you can consider it as a hybrid, but it's based on a Gaussian mixture. Okay? And so I'll talk about this one, and this one. This one we already covered it. Okay? Okay, so particle filters, you know, if you're doing it in MATLAB, you have a small model, you can do it in 5 lines. Just run forward. Once you get the data, update the weights, and run again. Okay? You're not touching the particles, you're just updating the weights. So the way it works, you have particles, run it forward. It's exactly as the ICAI. Then when you get data, update the weights. When you get closer to the data, you have more weights, and then rerun, and that's it. Okay, 2-3 lines. So they never work if you implement them this way. Why they are not working well? You know, consider the truth, and this is time. You start from a bunch of points, and you update it with a model. The data, when you get data, you're not touching the particles. You're just touching the weights. So the particles start moving away and away and away till they diverge. You will find one members having all the weights. We call it degeneracy of the particle filters. And all the other members just everywhere. So one particle takes the whole thing, all the weight, and the others are negligible. So it's like you're running forward model without any assimilation. Okay, and the filter collapse. So the most efficient way we found to make this work, they found, is by is resample. So every time when I get a place, I don't rerun from the distribution that I get, I resample. So I duplicate the members that are most likely, most close to the data, which in this case, I keep the ones that are close to the data and they will have more uniform weights. Okay? So, but there's still an issue that even with resampling, it's not working very well, and this was very nicely discussed by Snyder in 2008, is that when you have small number of particles, their weights cannot be well estimated because you're not representing the PDF very well. Okay? So you still require the PF a very large number of particles, and they, in principle, theoretically, they increase exponentially with the dimension. And we call this the curse of dimensionality. Okay? So even though, in 2007, Nakano, they compared it with the Lawrence 96. They took an ENKF and compared it with number of particles. This is RMSE, and as you see, they had to go to 65,000 with a 40 variables, Lawrence 96, to start beating the ENKF. I don't know what kind of ENKF they implemented because I'm surprised that is stagnating. I would redo that, and I'm sure we can, even the ENKF, we can still reduce it. Okay, but 65,000 with a 40 model variables. Imagine you have 10 to the 8th model. So there is a lot of research these days about it, how we can implement the particle filter to make it work with large dimensions. And I tried to put just this slide to explain, to organize this new direction. They try to push the particles towards the data. So, and this is Van Leuven is trying to do that. So they use future data to resample, so they keep the particles on the close to the data trajectory. And also, they try to do dimension reductions. So they, instead of putting the particle for the whole weight, they cut as local analysis or something, the dimension, and they apply the particles in steps. So they reduce the dimension. And so you will need less members. So more or less, this is where the community is trying to do, and all more or less trying to push towards the data so they don't diverge. Okay? I haven't seen yet a particle filter applied to a large dimensional system in ocean. And I saw a small application, a test lately from Germany. Lars Nerger, they compared the particle filter from Van Leuven with the ETKF, and the ETKF was beating it hand down. So there is a lot of research on it. And the question is, you have non-Gaussianity, but it's not only about representing non-Gaussianity, but are there data, you have enough data in the ocean to exploit this non-Gaussianity. So this is still something, how the interplay way between what's available in data to exploit this non-Gaussianity. Can we efficiently reduce the ocean state dimension? Is this, my main question is, and I'm a little bit skeptical about this, is that you're representing the whole PDF with 100 members, 200, 1,000. You're in dimension 10 to the 8. So how efficient you're representing this PDF? For me, I'm not convinced with that. Okay, you have a very large dimension. You cannot describe the PDF with 100 members. It's not a good representation. So how we will get something efficient from that is still to be demonstrated. Okay, I'm not saying it will not work, but it will not be very easy. Okay, if you go on the other hand to the Gaussian mixtures, the Gaussian mixture is representing the PDF with weight and a Gaussian mixture. Okay, so if this covariance matrix is very small, you get to the particle. Okay, so you get to the almost the Gaussian distribution would be very sharp, and the smaller is the covariance, the more it will look like a point. So if you take this, you get first we're still using the forward Monte Carlo step, whether it's particle filter, whether it's ENKF, and the idea here is to replace not Gaussian but few Gaussians. Okay, and then apply the update. And when you apply the update, you will have the Kalman update, and you will have a weight update. Okay, and the question where to resample from. So in terms of algorithm, it's the same thing as before, but it's like ENKF, but you have an update of the members, update of the weights, and we need to sample new members. Okay, and the weight of the Kalman update and the weights update is set by the covariance that you can control by the by how you estimate the covariance matrix of the mixture. So when you implement this, when you do this and you do it with a small ensemble, you will get basically the same issues that you face with the ensemble Kalman filter. Basically, you have an undersampled covariance. Okay, so you need inflation, you need localization, you need hybrid. The weights will still be inaccurately estimated. You have small ensembles. One simple way Stordal in 2011 is just make it by just nudge it and make it uniform. It's naive, but it works well. And the most important thing is resampling. If we resample randomly, as we're doing in the ENKF, we're just losing variance. And if you lose variance, it will not work very well. So Anderson, in 2000, if I remember correctly, did some kind of Gaussian mixture here from Anderson in 2000. And he was here putting all the data. So it's Lawrence 96 again, quarter of the data, half of the data, and all the data. Yes, this is Anderson. Yes, this is Anderson. This is the ENKF, regular ENKF, and this is what we did when we applied localization, inflation, and also we sampled. Not we sampled randomly, but we sampled from the first two moments of the distribution, mean and a covariance. We matched mean and a covariance. So basically, we're going from non-Gaussian. We get a non-Gaussian analysis, but we don't know how to sample from it. So we sample just the two moments. So we're losing the non-Gaussianity after analysis. But with that, we were able to make it beat very easily any ENKF. We're still not using the full non-Gaussianity. We're just using it at the update step. If you don't sample in a smart way, this is what you will get, and you will be way far from an ensemble Kalman filter. So the resampling was a key in there. So far, we're just matching the first two moments, but this is not enough, but this is what we were able to do. Okay? So what we're trying to do now is moving forward with this is we're trying not to put a Gaussian mixture on top of each particle. We're trying to cluster them. So we have less component in the mixture, and so the particles will die less. And we implemented it, as I would say, in a small, mid-size system, and it's working well. We never get to the ocean model yet. We need PhDs for volunteers, good volunteers, to go inside this big system and try these kind of things. So a quick discussion about non-Gaussian filtering. We're not there yet. We're still exploring. eNKF is working. It's difficult to beat. It's very robust. It works well. If you want to implement a non-Gaussian filtering, there are two things, in my opinion, that we need to be careful about. You want to parameterize the probability distribution, and you have to be really pragmatic. If you have 100 members, don't think you will be able to represent the whole PDF. I don't see how. Okay. The eNKF very smartly does this. It does a small ensemble in the forecast, and it applies Gaussian, so it keeps, there is a Kalman correction for each particle, so the particles do not collapse. Okay? It's suboptimal, but it's robust. And the main question is how best to sample a small ensemble from a given distribution. So far, we're still matching the first two moments. Is there a smarter way to do it? It's still a very open questions. Which features of the distribution we want to keep? It's a very open question, in my opinion. Okay? So this is basically where we are. I just try to closeness to optimality to classify the assimilation schemes. And very funny, I brought this from 2012. We're still more or less at the same place. So in 6 years, we didn't move really much, which surprised me. There is the Kalman filter, there is OIs. You can say the OIs are Kalman filters, but the covariance, you're not updating the covariances. There's particle filter. You take the particle filter and you take the Kalman correction and you get these ensemble Kalman filters. From there, you get the ensemble OIs. And this is where basically we are now. Okay? But we want to move higher up. So we started with these. We are moving to these. And the next step is how to move up. So now we are kind of here. Okay? Operational centers are working around here. And how we move up from this side or this side. Okay? More or less, these are the main things. And this is the same slide I showed 5 years ago. The only difference, I would say, the progress we made is that we can now use these to beat the ensemble Kalman filter with small systems. So in 5, 6 years, 10 years, we were able to beat the ensemble Kalman filter with small systems. It's still not demonstrated with the big systems. Okay? And this is where, more or less, the state of the art. So some remaining challenges in Bayesian filtering very quickly. It would be good to improve the parameterization of the ensemble covariance matrix, better inflation, better localization. There is no reason why you want to inflate the whole system everywhere or localize it in the same way with the same scales everywhere. So adaptive localization, adaptive inflation, there are techniques that we proposed, and it's still, we're not converged yet over there. Fault-free eNKFs is useful and is becoming more and more useful in the sense that some of the members will blow up. And the more members you will use, the more you will see that, and you have to develop a machinery for that. Non-Gaussian filtering, we know it's useful. But for which features, and especially the question at which cost? If I will use a huge machine just to get a little bit of improvement of the eNKF, what's the point? How best to resample small ensembles is really an open question. Imposing dynamical constraints on the eNKF, I saw a paper in 2017 trying to do that. Taking ideas from the variational community. How to best to handle model errors, I have a slide on that later on. Still a very open questions. And how best to handle multi-scale variability. When you do localization, you're just cutting everything that is not local, and you're losing some information. Can you do it in a smart multi-scale fashion? So these are very interesting questions, and each of them can be a big study by itself. Okay? Okay, so now I have one slide by slide, so overshooting everywhere. Bear with me, you'll have lunch in 15 minutes. Just get the big idea of what's going on. So Ensemble Kalman smoothing, I went to the master, Mark Bouquet of Ensemble Kalman Smoother. I told him I have one slide to present it. How would you do it? And he came up with a very nice way to present it. So what is Ensemble Kalman smoothing? It's Ensemble Kalman filtering, but I want to add future data. So I want to constrain the state with the future data. And there are different flavors. Whether you do it over a window, whether you look for initial conditions, or whether you do it as a fixed lag. What's fixed lag? And this is a must, people must use. So I will just give you the algorithm how this works. The fixed lag is I want to estimate the state at time n using L future data. Okay, L is the lag. So every time I move and update the state with plus L data. So basically, if you look at the okay, what I did here is not showing up. 1 second. I just wanted to show you this figure. I did something wrong. Hide on next mouse click. Let's see if it works now. Okay. Okay, so this is a figure I wanted to show. Basically, it represents what's going on. Is L equal 4 here? So every time I'm using the data to update the new data to update backward. 4 steps. Okay? So once I got more than 4, I get to 4 steps backward. Okay? This is exactly depicting what's going on in the smoother. I use the future L data to update backward. So if you want to implement this, it's surprisingly simple. Okay? So there are 2 ways. One straightforward way is that I will put all the states backward to L in one big state vector and apply the NKF as usual, if you want to put yourself in a Gaussian assumption. A more very elegant way is, you remember how we go from the analysis ensemble, from the analysis forecast to analysis ensemble through this transformation matrix? Okay? You can go from the analysis ensemble at time k to the smoothing ensemble at time k just by multiplying with these transformation matrices. So it's very simple. Just save this matrix and save this ensemble. It's a small matrix. You can save it. The issue is that you have to save all these ensembles, and this becomes expensive. Otherwise, you get it almost for free. But there is a problem with storage. Okay? So you can come back. So basically what happens, there is an ENKF forward, and then you can go backward just by using the transformation matrices and compute the smoothing if you want to include more information in your estimate. It's good for reanalysis. Okay? So it's computation cheap, but the storage is the main issue in here. You might think also about, when you get the data future, you can come back, update, and reforecast. This is what Kanley did. She calls it RIP, running in place. So she does this and she reforecast. And she said that in the paper when they presented it as an empirical scheme. Actually, what we show in the paper will show up in 2018 in monthly weather review, that it's not empirical, it's really Bayesian consistent. So you can go back and rerun, and you will get a better background to do the update. So it helps. And it's not empirical. Okay? This is the smoothing. This is only a slide. So if you are interested in doing reanalysis, you can apply this, and it's quite doable. Okay, this is a whole mess. Hybrid methods. So hybrid methods, probably you're hearing about it, and it's becoming popular in the atmospheric community. I haven't seen applications of it in the ocean community yet. But so the idea of this hybrid method is to make the best of the ensemble methods and of the variational methods, 3D var and 4D var. And there are a lot of flavors. I try to make some sense of them. One flavor is we call ENDA, Ensemble of Data Assimilation. So basically, you have an ensemble of 3D var or ensemble of 4D var running. Okay? You do an ensemble of 4D var. It's expensive, but you can do ensemble of 3D var, ensemble of 4D var. The hybrid ENKF, this is what I talked about before, is just using, when you get the covariance of the ensemble, you add to it a static background, and you apply the Kalman update as usual. E3D var, E4D var is basically get a hybrid covariance and put it in 4D var or 3D var. Okay? So the ENCAF will update the uncertainties. This is what's one of its advantages. And 4D var can do the smoothing with an updated covariance. And lastly, what they call EN 3D var, EN 4D var are basically this, but instead of using the adjoint in 4D var, they do reduced adjoint in the ensemble space. Okay, so they avoid the adjoint. But there is an issue which is in the localization. It's not clear yet how they can localize. There is 2017 paper, Bouquet told me about it, that I didn't have the time to read it, but they discuss how we can do that in EN 4D var. So basically, these are the hybrid methods, and based on what we know now, they make sense, okay? And if you know the basics of 3D var, ENCAF, and they are solving the same thing, they are developed around these. Okay, I will move quickly to state parameters estimation in the ENCAF. Someone asked me a question about it. How we do state parameters estimation. If you want to do, you're interested in the state, but also in the parameters or the inputs. Okay? And it could be useful, if you're doing wave data assimilation and you do the initial condition, but the wind is blowing in the other direction. Okay? No matter how you assimilate, the wind will take the wave somewhere else. So basically, you want to estimate, improve what is most important for your predictability. And it's not always the initial condition. Some parameters can be important in some situations. Okay? 4D var does it very well and very easily. You just control the initial condition with the parameters. This is what I showed with echo. And filtering can be also done in a straightforward way, and this is what the reservoir community has been working on for like 10 years. And it's just put the state and the parameters in one vector. So we call it joint state parameter estimation. Okay? So, and then you apply the ENCAF as usual. So basically, if you want to see how it works, I have a new state that's made of the state and the parameters I want to estimate. So I build a new state space model where I have constant dynamics of the parameter. So the parameter is predicted with a constant dynamics because it's constant. Okay, and then I apply exactly the same machinery as ENCAF. So it's very straightforward to apply. And they are using it successfully with reservoir models because they need to estimate the permeability under the ground, and it's a 3D field. So if you go to the literature in the reservoir community and hydrology, the dual, instead of the joint, they developed what they call dual filtering. And the idea is to run two filters at the same time, one for parameters, one for the state, to separate them. So they run first the parameters, they estimate the parameters first, and they use these parameters to forecast the state, and then they update the state again. And they say this helps a lot for a problem related to inconsistency, because when you put them together, the parameter is affecting the state in the future, not now. So they may be, with the cross correlations, a small ensemble, it might not be good to do that, and it creates some inconsistency. So very often they go back and rerun. And you can do this very well, but you're making two forecast steps, not one. And it's very popular in the reservoir community. Smoothing, you can also do it as for diverse, just put them together and run it. Now this slide, forget what I wrote here, just look at the title. State hyperparameters estimation. One thing that ENCAF can do, or filtering framework can do, is to estimate hyperparameters as well when we're running the filter. And what hyperparameters are the parameters of the distribution. So, and for instance, for us, it is like, for instance, if you want to estimate the variance of the model error or the variance of the observational error, there are techniques to do that online while the filter is operating. It becomes a little bit nasty and a lot of equations, but keep in mind you can do state hyperparameters estimation if you don't know the observational error, the variance of the observational error. It can be done, and the most popular is what we call the expectation maximization approach, but it requires some iteration on the smoother. Okay, so just keep this in mind. Now I have two slides, and we'll finish with these developments. Model errors. And I think it's still a very open question. So what I'll show you is just, I'll talk about is just some thoughts, they are not, from what I understand, because I think the problem is still very, very open. How we treat model errors. Is it the best way to put a covariance model Q and put everything on it? I'm not very convinced with that. It's a very large matrix. Not only that, but it doesn't have dynamics neither. And this can be dangerous. And it will increase the rank anyway, so you don't want to do that. So inflation is naive. It's just replacing Q. You're inflating what's missing. And it's really efficient, surprisingly. But if you inflate too much, also is not good, because you're inflating with the wrong correlations. If you have perturbations like on the forcing, an ensemble of forcing, this will give enough spread and will include in the system uncertainties coming from the forcing. So use them. So you will rely less on inflation, and it will give you better correlations that representing the uncertainties in the forcing. If not, you might think about also estimating the forcing as part of the assimilation system. Dynamical constraints, in my opinion, are very, very important, and so far we're not imposing them in any estimate of the model errors we are doing, so this should be used whenever possible. One way to do that is to do it through state parameter estimations. The parameterizations we're doing in the ocean, as they are representing what's missing in the model. So why we're not estimating viscosity, diffusivity, I don't know, any parameterization schemes, we can try to estimate the parameters, and we can do it offline. And also with the 4D VAR or with the filters. Detlef Stammer did it with 4D VAR. He estimated viscosity and diffusivity. And these, I think they deserve much more attention before starting thinking about estimating the covariance model of the error. There are also other approaches that people are working on it, and I've seen Van Leuven giving a talk last year about it, is you take the increments, have XA equal XF plus the update. You take all this update, and you try to fit it to some physics. So you try to see if there are some physics missing that you can put it back in the ocean. So there is some physical parameterization inside, and it looked like a very good idea. He was trying it in a very simple model. So once you optimize your parameters and you use ensemble forcing and these things, you might start thinking about estimating the variance of the model error, and you might think about using some state hyperparameters estimation. But first, reduce the error, make it as physical, the model error as physical as possible, and then later on start thinking about this random noise that is supposed to be unbiased, which is not true now. Okay? Last slide about, and then I'll show you a few movies that look cool, about coupled data assimilation. So now, if it's becoming very, very popular these days, they want to do coupled data assimilation in the sense we have ocean model, we have atmospheric model, and we want to do assimilation to both at the same time. The same thing for biology. We show the talk. So you have the biologically coupled to the physics, and you want to use the data in the biology to also improve my physics and vice versa. So technically, you consider the system as one. As in state parameters, you put one system, but now the other component has dynamics. So it's one system. You forecast and you update. Okay, it looks easy. It's one system. So we call this strong CDA. So any data in the ocean or the atmosphere, even at 5-meter height, will affect the ocean. And a much easier way to do it, and they came up with a word for it so that it becomes legal. It's called weak CDA, weak data assimilation coupling. Basically, run assimilation up, run assimilation down, and let the physics exchange the information. I wouldn't call it CDA. It's just this is standard assimilation for each one, and the coupling is done through the physics. Okay, so if you hear someone saying weak CDA is just running each one separately. Okay, the challenges of this problem is that in the correlations, when you do the correlation, what kind of information, how representative the correlations are of this turbulent boundary layer. It's very turbulent, and can E and KF pass the information from one system to the other in a very efficient way? What correlation I should keep? What kind of vertical localization I should use? Should I use lag correlations because the atmosphere and the ocean can affect each other, not at the same instant, but later on? So there are studies with simple models trying to make sense of the correlation and what correlation we should use to pass the information in between. It's still a very open question. But you will probably need all these, non-Gaussian state parameters, model errors in there. There's also a big bias in the coupled models yet. So it's still a very new field to work on. Okay, so all these are still open questions you might consider working on. I will finish with 5 minutes on 3 minutes, let's say, on what are our plans in the Red Sea. And so far, what I showed you in the Red Sea, we implemented successfully these deterministic ENKFs. We made it fault-free. We can run thousands of members at the same time. We didn't do dynamical consistency. This is something we are quite interested in, and we'll start working on it with a new members that is joining us in a couple of months. I still think that the stochastic ENKF is a better formation. It samples randomly, but you can do it in such a way to sample the observational or deterministically and match the mean and the covariance, so you don't lose variance. Okay, and we did that in 15, in monthly weather review, and this is something I would like to implement on the big system. It can accommodate hybrid and localization in a much better way than the DNKF because of the implicit resampling. State parameter is something we want to do, and we're working now very hardly on coupled. So now we coupled Ocean MIT GCM with WRF, working with the Scripps people. We have Ensemble with MIT GCM. We're working on Ensemble with WRF. And once we get these, hopefully next year, we'll start working on coupling the two ensembles and start trying the system. Of course, we want to move to non-Gaussian, but also we were testing ENOIs and how good they are and what we can do with them. And I'll show you an example. Last year, we requested 50 million core hours, and now they want to make us feel guilty about all the CPUs we're burning. So now when we request number of CPUs, they tell us how much money this is costing. So for 50 million core hours, it's 650,000 K. This year, we're requesting 300 million core hours for this year because we want to run 1,000 members, we want to run 10,000 members. And this will go up to several $1 million. So running ENOI without updating the members can burn this by 100 or 1,000. Okay, and you can implement it and try it. It works pretty well, actually. And we're trying to improve upon that. So instead of getting a covariance that is fixed in time, we can make it vary per month. We thought about doing it in an adaptive way. Imagine you have a big dictionary of all possible realization of the ocean. So when you get a forecast, you start looking for the uncertainties from the dictionary. So if you have an ensemble that hand-picked according to the current variability without integrating forward. It's just sitting and dictionary. From the dictionary, you pick it up. From this, we will definitely go to some hybrid. We have a covariance that is fixed, covariance that is varying, and make a hybrid of it. They are very efficient, these methods, surprisingly very efficient. And here we're still on, I would say, we're still working on it, but still in experimental phase. We're not there yet. We have GM clustering, and also, as everyone was working on, particle filtering, multiple particle filtering. I'm more optimistic about this one than this one, but I might be proving wrong also. Okay? And so it's not clear where it's going to go there yet at all. So once you have the assimilation system set, you start thinking about cool stuff. And cool stuff is this, we're calling it Virtual Red Sea Initiative. It's with MIT, Scripps, and PML. And we're trying to make sense of all this data. We're getting ensembles of these data, how to analyze the ensembles, what kind of information we can extract from the, of the ensembles. Can we do machine learning on uncertain data? Can we do statistical learning? Can we do cool visualization with these? I'll show you an example. This is what we will be focusing on in the next 3 years. The idea is you have data, you have models, and you have products, okay? And what kind of products you will give. This is an example. This is simple, a regular atlas where you put wind, waves, and you can start thinking about doing energy. We're adding to it with PML chlorophyll, phenology, atmosphere. So the idea to put everything and do annotated statistics right away just by clicking a point, okay? This is another example how to visualize ensembles and do it online. So basically here you have 6 months or 1 year, I don't remember, of ensembles, 100 members. And when you put the point at the mouse at one point is computing with GPUs the statistics, the distribution, and plotting it. So you can choose to see mean, you do any statistics and then compute with these cool GPUs. Don't ask me how they did it. Very smart PhD student we had to graduate, unfortunately, and he went to Delft. But you can see the evolution of the standard deviation, you can see the evolution of the mean, you can see the evolution of the mode. Just by clicking, moving the mouse, you can start seeing the distribution at every point. Just it's computed online. Something I like quite well, you can do risk assessment, someone sitting in his office. He doesn't need to read the ensembles, he doesn't need to upload the ensembles. Like for instance, assuming you want to put a desalination center, Aramco wants to build the biggest refinery worldwide on the Red Sea, so they want to pump 500,000 meter cube of water per hour. This water needs to be less than 30 degrees so that it's cool enough to cool the refinery. And the question is where the temperature is always at 30 degrees. So basically, you can just move the mouse. This is the threshold, 30 degrees. And accordingly, you see the areas where you can pump and the areas you cannot pump. You can even go further without, just a mouse. You want to compare 2 time series. One, okay, this is my location, my reference. What if I start pumping from another point? So what you will see here, you will see 2 time series. These are uncertainties. And if they are not symmetric, the distribution is not Gaussian. So these glitches represent uncertainties. And you can start comparing, just moving the mouse, the time series at every point compared to this one. And you can decide this is a good point to pump from, and this is not a good point. And it's a full time series. Last example I think I have, this is, you have an ensemble of velocities. So the question is not where the particle will go, but the question is which probability the particle will go. And just again, by clicking off a point, what you're seeing is probabilities where the particles that we are unleashing will basically go. So at the beginning, there is a good predictability, almost it will stay here. Later on, after 2 weeks, it can go anywhere and just forget it. Like, for instance, when you click here, you will see that it's very likely will follow a boundary current, but later on, it can go from this direction, and we cannot tell you where. So the uncertainties you're getting from these filters can be very widely, very smartly, and used. This is the last example. If you want to, for instance, look at the pathways for chips or AUVs, so basically what you're doing here, just by moving these nodal points, by moving, you're seeing the time series of any data right away with the uncertainties on top of it, and accordingly, you can decide where to go. So basically, this is what I wanted to show you. Thank you very much. I like this visualization because I just wanted to finish with that. This is what we used to, as what I showed in the first lecture, and some people, oh, okay, model error. And this is how our administration used to look at us. And when we started showing this visualization and what we can do with these ensembles and these things, and here an example, I think we're showing probability distribution, running probability distributions. This is at every point how the distribution will look like. They started liking us very well. Oh, I'm taped, so maybe you should not show this. But it's really helping us to present what we're saying, what these uncertainties are useful for, and you can use them to do some cool stuff with it. Okay? Thank you very much.